right, welcome to the Explainer. Today, we're going to pull back the curtain on machine learning. We're going to look right under the hood to see how we actually teach computers to think, what's going on inside those artificial brains, and we're going to tackle this really fascinating and kind of unsettling question of why, sometimes, their own creators don't even know how they work.
So, let's start with the absolute basics. Computers are incredible at following instructions. You give them a program, a set of rules, and they will execute those rules perfectly and at a speed that's just mind-boggling. That's traditional computing in a nutshell.
But that idea opens up a much bigger question. What if we didn't have to write a rule for every single little thing? I mean, could we actually build a system that learns from its own experience, one that gets better all by itself?
And you know what? This isn't a new idea. This very question was nailed way back in 1959 by an AI pioneer named Arthur Samuel. His definition of machine learning is still spot on. The whole point isn't to just program the right answer, it's to give the computer the power to find the answer on its own.
Okay, so let's get into the fundamentals. What does this whole teaching process actually look like? How do you go from just a huge pile of data to an AI that can make some genuinely smart predictions?
Well, when you boil it all down, machine learning is really just a superpowered form of pattern recognition. The system chews through massive amounts of data, hunts for any patterns it can find, and then uses that knowledge to make predictions about new stuff it's never seen before. And here's the key. The more data it gets, the smarter it becomes.
You know, the perfect way to think about this is how you teach a little kid. You wouldn't sit down and write a rule book for them about whisker length or ear shapes. Nope, you just show them picture after picture, saying, that's a cat, that one's a dog. And after a while, their brain just kind of figures it out. It builds its own internal model. Machine learning works on pretty much that exact same principle. It learns by example.
And if we stick with that teaching analogy, it makes perfect sense that just like there are different ways to teach people, machines have a few different ways to learn too. And the method you choose really just depends on what kind of data you have and what you're trying to do.
So, the most common style by far is called supervised learning. This is exactly our cat and dog example. You give the machine a huge data set where every single thing is already labeled with the correct answer. It's basically learning from an answer key, figuring out the connections between the input and the right output. Okay, but what if you don't have an answer key? What if you just have a mountain of data with no labels at all? Well, that's where unsupervised learning comes in. You just dump the data in, and the model's job is to find the hidden patterns all by itself. So it might not know the words cat or dog, but it could definitely sort all the images into two different piles based on what they look like.
And then there's the third style, reinforcement learning. This one is all about learning from consequences. The best example is an AI learning to play a video game. Every time it makes a good move, it gets points. That's a reward. Makes a bad move, it loses points, a penalty. And after playing millions and millions of games, it figures out the best strategy to get the highest score, all through pure trial and error. Now, to handle really complicated patterns, I'm talking about understanding human speech or recognizing one specific face in a massive crowd. We needed something way more sophisticated. So naturally, engineers looked for inspiration in the most powerful learning machine we know of, the human brain.
The whole journey started with one tiny, simple component called a perceptron. Just think of it as a single artificial neuron. It takes in some information, decides how important each piece is, and then spits out a simple yes or no answer. By itself, it's not that smart.
But here is where the magic happens. You take one of those simple little neurons, and it's not much. But when you start connecting thousands or even millions of them together, you get an artificial neural network. You have an input layer where the data comes in, an output layer where the answer comes out, and these hidden layers in the middle where all the heavy lifting and complex thinking happens. And when you start stacking a lot of these hidden layers on top of each other, well, that's what everyone's talking about when they say deep learning. And the genius here is that each layer learns to recognize something more complex than the last. So the first layer might just see basic edges and colors, the next layer might combine those into shapes like eyes and noses, and a layer after that might put all of that together to recognize a whole face. It's this hierarchy that lets them understand really abstract ideas.
Okay, so we've built this big, complicated, brain-like structure. We get it, but how does it actually learn? How does it go from just a random mess of connections to a finely tuned machine that can actually get things right? The secret is in how it adjusts itself when it gets something wrong. The main process is a mathematical technique called gradient descent. The slide here has the perfect analogy. Just imagine the model starts out at some random high spot in a valley. That represents a state of high error. Its answers are way off. The goal is to get to the very bottom of that valley, the point with the absolute lowest error. So it looks around, finds the steepest path downhill, and takes a little step. That step size is called the learning rate, and it just does that over and over again. Take a step, check the slope, take another step, until it finally settles at the bottom, where it's found the best possible solution.
So this whole idea of building deep neural networks has been unbelievably powerful. It's been a total game changer. But as these networks have gotten bigger and more complex, their very nature has created a really significant problem for us.
You see, a deep neural network might give you the right answer with stunning, almost perfect accuracy. But when you turn around and ask it, okay, how did you know that? You get nothing, just silence. Its logic is buried in this tangled web of millions of tiny mathematical adjustments, a process that is just way too complicated for any human to follow. And this is famously known as the black box problem. We can see the data that goes in, we can see the final answer that comes out, but the whole decision-making process in the middle is a complete mystery. Now, if you're just recommending a movie, who cares? But if it's being used for a medical diagnosis or a loan application, yeah, that's a huge problem for trust and accountability. And what's really unsettling about these black boxes is just how fragile they can be. Researchers discovered something called an adversarial example, and this is just wild. They took a picture that a network knew with high confidence was a panda. Then they added a layer of digital noise to it that's so subtle, you and I can't even see it. And the result? The network suddenly became over 99% confident that this was a picture of a gibbon. It's just a stark reminder that these systems do not see the world the same way we do.
So yeah, this whole black box issue is a major hurdle. If we're ever going to truly trust AI with the really important decisions in our lives, we have to find a way to make its thinking transparent. We've got to open the box. And this absolute necessity has given birth to a whole new field of research, explainable AI, or XAI for short. Its entire goal is to develop methods and models that can peel back those complex layers and actually show us the why behind an AI's decision.
And one of the coolest XAI techniques is called a class activation heat map. It's basically a visual overlay that shows us exactly which pixels in an image were most important for the AI's final call. So in this picture, to identify an elephant, you can see the model is lighting up right on the shape and the texture of the animals, exactly where a person would look. This kind of transparency is how we build trust, and it's absolutely essential for figuring out what went wrong when a model makes a mistake.
Because ultimately, this whole journey with machine learning isn't just a race for more power or better accuracy. At its heart, it's a quest for trust. As we weave these incredible tools deeper and deeper into the fabric of our society, making sure we can always turn to them and ask why, and actually get a good answer, well, that's not just a technical challenge. It's one of the most important tasks of our time.